Welcome. In this video, I will state and prove a formula that I call the annuity formula. What an annuity is a regular payment with in general two purposes. The first is if you take a loan and you're trying to make payments on that loan, or you're trying to save up money and you're trying to put the money towards that savings. Okay, so you have annuity loans and annuity savings. The formula states that the capital I have after n terms, periods, is going to be the initial capital plus the annuity divided by the interests are to the multiplied by 1 plus the interests to the power of n minus the annuity divided by the interests. So this is the formula. Right? All right. Now I want to prove this formula. To that end, I want to start by stating and proving a lemma. All right, and this lemma is related to a geometric series. Right. So a geometric series says if I have a sum which consists of consecutive powers of some number, I can actually write this sum as the x to the power of n plus 1 to the next power minus 1 divided by x minus 1. Right? So this is what I want to prove first before I go back to the proof of the original statement. All right? Well, what I do is I take this thing here, this construction here, this sum here, and then I multiply it by 1x. All right? So I check what happens if I take x and multiply it by s. Well, 1 times x is just x. X times x is x squared. X squared plus x is x cubed plus x to the power of n plus, n, and then x to the power of n plus 1, right? But if you look closely, what this is exactly the same as s, because we have x squared, we have x cubed, all the way up to xn. So this whole thing here is part of s. But what are we missing? Well, we're missing this little 1 over here, all right? So this is actually just s minus 1, and then this extra little term over here. Okay? So, by isolating s and this new expression here, I can actually figure out the formula for s. All right? So I have x times s, and then I subtract s from the right-hand side and left-hand side. Well, what I'm left with on the right-hand side is just x to the power of n plus 1 minus 1. Right? I have a common factor of s here. So what this says is it says, okay, s times x minus 1 is equal to x to the power of n plus 1 minus 1. All right? Now I can divide on both sides of the equation here to isolate s, and what I end up with is n plus 1 minus 1 over x minus 1, which is exactly what I wanted. Right? Okay. So remember this result, that I can write this weird little geometric series looking thing as this fraction instead. And this is beautiful, because let's say that you have 100 terms here, I can just calculate it as one fraction. It's way easier, right? So we'll get back to that when we get back to the proof. So remember this lemma here, all right? Beautiful. So now let's look at our annuities, all right? So let's say we have some initial capital at C0. Okay. So at the start of the process, I have some initial capital, C0. All right? After one term, after one period, I will have, this initial capital will have accrued interests. That's what this is. And then I add one annuity. So at the start of the first term, or after the first term, the initial capital will have accrued some interests, and I'll have added an annuity. All right? Let's check what happens after the second period. All right? All right. We take the C1 and we add interests and we add an annuity. Right? So it's the same exact process here. All right? But let's figure out, what is this actually? Well, the C1 is what it says up here. So that's the initial capital plus multiplied by the interests plus an annuity, and then I should multiply it by the interest and then add another annuity. All right? Well, let's expand this fraction by multiplying this in here and this over here. All right? So what we get here is we get C, the initial capital, and then 1 plus R. We have two of those, so that's squared. All right? Then we have the annuity plus the interest. Multiplied by the interest, and then plus the last annuity. All right? Hopefully, it's not a huge stretch to convince you guys that what happens here is that after n terms, we get the initial capital multiplied by the interest to the power of n, because each time we add the interest to the initial capital, but all these will accrue less interest because they were added later. Right? So only in the initial capital accrues all the interests, and all the following annuity payments will actually accrue less interest. All right? A, the annuity, is going to be a common factor in all of these terms here. Okay? So what I get here is I get the initial capital multiplied by the interest to the power of n, and then plus A. But then I'm going to write 1 plus R as A, just to make things a little bit simpler for me. All right? All right? So I have, I get a 1 from over here, so that's 1 plus A squared plus all the way up to A to the power of n minus 1. Well, doesn't that look familiar? It's exactly what our lemma was. This is like a geometric series type thing that our lemma made a statement about. So I can actually just replace this whole parenthesis here by that fraction we talked about earlier, all right? So this is the same as C0 times 1 plus R to the power n plus A, and then that fraction, well, what did the fraction say? Well, we take the highest exponent here and increase it by 1, all right? So A to the power of n minus 1 goes to A to the power of n minus 1 divided by A minus 1. Right? But what this actually is, if I put 1 plus R back in instead of A, this is the same as, say, 0, 1 plus R to the power of n, and then we have 1 plus R to the power of n minus 1 divided by 1 plus R minus 1, 1 plus R minus 1, so these ones just cancel, and we just have that nice little numerator there. Oh, shoot. I'm supposed to say plus A times that nice little guy. So these ones cancel. Beautiful. Now I move this R over to the A. So the R is the numerator and the denominator, and the A is the numerator. Okay? And then I get, say, 0, the initial capital, 1 plus the interest to the power n. And then I have plus A over R, A divided by this R in the denominator there. and then I multiply it by 1 plus r to the n. So that's this times this. But I also need to do the same thing where I multiply by minus 1. That's where I get this fraction from. Again, we see this beautiful little thing here where this term here and this term have a common factor of 1 plus r to the power of n. So we can put that outside a parenthesis, and what we end up with is the initial capital plus a over r multiplied by the interests to the power n minus a over r, which is exactly what we wanted to show. We wanted to show this. The beauty of this absolutely gorgeous formula is that this formula actually covers pretty much all conceivable cases of capital development, gains, loans, annuities. Because if, let's say that the annuity is 0, so the numerator here is 0, what we end up with is the compound interest formula. Isn't that wonderful? All right. Let's say that we're doing we're just looking at annuity savings. Let's say we're starting fresh. We're starting from 0. We're doing an annuity savings from scratch, right? That means that the C0 is 0. Okay. Well, what do we end up with? Well, then we end up with this gorgeous little thing. We actually just end up with what we were looking at earlier. We end up with this times, you end up with a times 1 plus r to the power of n minus 1 over r. So this is the annuity savings formula that some of you may have seen. What if we have an annuity loan? Well, an annuity loan is just an annuity where the initial capital is negative, and that is the only difference, really. So that means that we have some negative number here, 0 minus a 0 plus a over r. 1 plus r to the power of n minus a over r. All right. Of course, you're not going to have the same. Usually, you will not have the same interests if you have a negative balance or compared to a positive balance. But then you just change what the interest rates are as soon as you cross that balance, and this formula will still be completely valid. Yeah. In this last case here, one way to actually deal with this is some formulas will actually state what the annuity will be under these terms. And in this case, you actually want the initial the final capital to be 0. You want to know when your capital reaches 0, which is when you have paid back your loan, right? So this is for the annuity loan formula. You actually want to put the final capital at 0. All right. So then we get that a over r is equal to this whole thing. So that's minus this, or let's just keep this. It's just a negative number plus a over r times 1 plus r to the power of n. Well, how do I yeah. In reality, we don't want to do this. In reality, we want to do the same thing as we did up here, where this is 0 and we have this thing. Right? So let's re-expand this weird little thing here. And then we have plus A over R, 1 plus R to the n minus 1, right? And we want to, the goal here is to isolate A, or the annuity, right? So, so these two things will be equal, and what we can do now is we can actually put these terms, make these terms equal. So, so we have that C0 of 1 plus R to the n is going to be the same thing as A multiplied by 1 minus 1 plus R to the n over R. And I flipped these two because these two must have opposite signs for this to be true, right? And now I just divide by this little beauty over here, right? So the annuity will be equal to the initial capital multiplied by 1 plus R to the n times R over 1 minus 1 plus R to the n. And what we can do now is we can multiply by this, the reciprocal of this in the numerator and the denominator, and we can multiply by 1 plus R to the minus n here and here. This will cancel with this, and this will cancel with this, and what we end up with is the initial capital, the loan amount, times R over 1 plus R to the power of minus 1 minus 1. And you may be familiar with this formula for the to calculate the annuity when you know all the other conditions on the loan. Right? So these are two simple corollaries or results that follow pretty immediately from this formula here. But you don't actually have to use any of these. This formula will do all the heavy lifting, regardless of what the situation is with your annuity. Well, hopefully that was enlightening in any kind of way. If you have any questions or comments, just leave them down below.